In previous videos, we saw why sequential I/O is important for large-scale training and how we can use WebDataset to read sequential datasets stored as POSIX tar files. Let us now look at how we can create such datasets. Recall that a WebDataset is just a tar file, and within that tar file, consecutive files with a common base name make up a training sample. So how do we create such tar files? The simplest case is if the file-based directory structure of a training set already conforms to the naming conventions of WebDataset. For example, in speech recognition and OCR, we frequently store training samples as pairs of files. One file contains the image or audio, the second file contains the textual transcription. Files that make up a training sample share the same base name, but have different extensions. If your file-based dataset has a layout like this, you can create a web dataset simply by creating a tar archive in which the entries are sorted alphabetically. You can do this by using GNU tar with the --sort equal name option, or with other kinds of tar implementations. You can generate first a sorted list of file names and then use the -t option to actually add those files to the tar archive in order. Note that for WebDataset, the base name of a file is the file name with all extensions removed, not just the last extension removed. For example, in an image segmentation task, we might store input images under basename.input.png and segmentation targets as basename.seg.png. The base name is the key for the training sample, and input.png and seg.png become the dictionary entries for the actual image data. Using commands like tar-sorted will not result in a sharded or shuffled dataset, but we generally want to shard and shuffle datasets prior to training. Fortunately, we can leave these operations to other tools connected via pipelines. For example, the tarp command provides inline shuffling and splitting for POSIX tar archives. The tarp split command can even upload shards to the cloud. Here, the first command pipeline will generate a shuffled dataset on local disk, and it will split it into multiple shards. The second command pipeline will generate a shuffled dataset and split it into shards and upload those shards into a cloud bucket. This pipeline will actually never consume any additional local disk storage. Let us look at some other ways in which file-based datasets are stored and how we can convert them to a web dataset. Imagenet is a typical example. It is usually distributed as a large collection of individual image files, together with a single file containing metadata and class information. This is a common representation of image datasets because it speeds up loading for file-based data loaders and because it makes manipulating class labels easy. It also has some disadvantages, since the metadata file always needs to be around and generally is loaded into memory, so it consumes a lot of memory. This style of dataset is easy to replicate directly with WebDataset. We start by making a list of all the files we want to put into the WebDataset. We can perform all the shuffling and splitting at the file name level before creating the tar archives. For this demo, we just create a single small shard consisting of 100 images. Now we can create the WebDataset out of the file list by using the -t option to tar. We're actually storing absolute path names, and tar removes the leading slash. The exact paths don't matter as far as WebDataset is concerned, since it only relies on distinct base names. If we try to read the resulting tar file with a WebDataset class, we only get the base name and the image content, but no associated class. That's because the class was not actually stored in the tar file. As with a regular file-based dataset, for this style of web dataset, we need to associate the class information with image files dynamically. Here we read the metadata using an Imagenet metadata class. Then we use the map method on dataset to map a small function over each sample that looks up the class corresponding to the key and adds it to the sample. After we've done this, we obtain a regular iterable dataset returning tuples consisting of an image and the corresponding class label. The previous method is the most similar to the way file-based datasets like Imagenet are used right now. However, this is not a good solution for very large datasets, since the metadata or class label data itself can be very large. It is generally preferable to store both inputs and targets for training as separate files directly in the tar archive. We've already seen this layout above where the data was arranged like that on disk in the file system. We could, of course, rearrange our data files to have the desired layout in the file system and then use tar-sorted as before. But this is slow and it requires lots of extra storage. Instead, what we do is that we create a recipe that describes how to put together the tar archives we want from scattered files and content. Then we use the tarp create command to actually create the tar archive from that recipe. Recipes used by tarp create contain lines consisting of two fields. The first field is the file name that the content is stored under in the tar archive. The second field is the source of the content that is stored in the tar archive. There are three kinds of sources that tarp create recognizes. File : reads a local file. In fact, you can also just use a path without any prefix. Text : adds the following text as a literal content of a file. And pipe : runs the given command and adds its output to the tar file. You can use this for accessing object stores, retrieve files via SSH, perform on-the-fly conversions, or even perform data augmentation. So in this example, the source for the first JPEG file is the output of gsutil cat of some file that is stored in a Google Cloud bucket. So we first need to build a recipe file. Here's a simple Python script that does this. Note how we use the same metadata instance to look up classes corresponding to each image file, and then add that information into the recipe. Here you see the output from this simple script. It describes how images are copied into the tar archive from path names on disk, and how class labels are entered directly as text. To create the tar archive, we use the tarp create command. It looks through the recipe a line at a time, retrieves the file contents based on the second field, and then adds it to the tar file under the name specified in the first field of each line. We can look at the resulting tar archive and verify that it has the structure we expect. These data files can now be used directly for training with WebDataset. Since each tar file is self-contained, we do not need to load any metadata, and we can be certain that the class labels and metadata associated with each image are correct. All the previous methods of dataset creation relied on command line programs for creating the tar archives, either the tar command or the tarp command. But we can also create such tar archives using the WebDataset library itself. The library contains two classes for writing tar files. Tar writer just takes samples as dictionaries and writes them out sequentially to a tar archive on disk. Shard writer is similar to tar writer, but it splits the output into multiple .tar files, ensuring that each archive is smaller than a given byte size and has fewer than a given number of samples. First, let's iterate over the files in the Imagenet dataset using Python. This code actually has nothing per se to do with WebDataset. It is simply what is necessary to iterate over files stored in a directory in the file system. Iterating over the files of a dataset is actually much simpler using WebDataset than using file system primitives. Once we have an iterator over the files on disk, it is now very easy to write them to disk using the shardWriter class as a tar file. Here, for illustration, we've set a maximum shard size of 50 samples. Of course, in real applications, we would pick much larger shard sizes. As before, we can verify that the data is stored correctly in the tar archive by just using the standard tar command. Training on this dataset works the same way as before. That is, we can just open the shard and obtain pairs of images and corresponding class labels. In the previous example, we used shardWriter to write binary file contents of data read from disk. But the shardWriter class can also be used to compress and write image tensors and other numerical data directly. This makes for particularly simple conversion pipelines in many cases. Let's illustrate this by converting the Street View house number dataset to WebDataset format. We first open the TorchVision dataset as if we were going to train on it. Conversion is now particularly simple since the Street View house number iterator gives us the data we need one sample at a time. So all we need to do is construct a sample dictionary and tell the sync, the shard writer, to write it to disk. As you can see, the output was generated correctly, and we end up with a tar file that contains pairs of files, one file containing the class, the second file containing the image. In summary, we've seen several easy ways of creating datasets that we can read efficiently with WebDataset. We can use the tar command for the images and then use a separate metadata file for the class information. Or we can use the tar command on a directory tree that contains pairs of image and class files. Or we can use the tarp command with a recipe file. Or we can walk a directory tree in Python and write the binary data with a shard writer class. Or we can use an existing PyTorch dataset and then write the decoded samples with a shard writer. There are many other ways, since datasets for WebDataset are just regular .tar files.